Okay, doing a little start of the recording volume check, and we will start in 172 seconds. We get to look at these warm-ups. Go. Alright, it is time to begin. I gotta just mute the alarm that I forgot to turn off here. Okay, there we go. Let's see. Yeah, let's do that. Alright, so there are two warm-ups here. These are the ones just shown right at the end of class on Thursday, just to try to preview. So we've got here first the integral of 20x to the 19th dx. That is, in other words, asking what should you differentiate in order to get 20x to the 19th, right? We're always thinking about going backwards now. And then the second question, again, isn't to differentiate itself. It's the derivative of what? Fill in the blank. The derivative of something would be 1 over x. We'll do those warm-ups in just a second. I actually would like to, if I have, let me just check my slides. Yeah, I do have that. I wanted to do as much as possible announcements both at the beginning and at the end, just because of when people might be joining or just kind of scrolling through recordings and such. So sort of a typical week with a quiz on Tuesday and Thursday. I am trying to get the WebWorks scores uploaded, but this morning there seems to be a bit of a lag in Canvas, so even uploading exam scores took something like 10 minutes, and exam scores normally only take maybe 20 seconds to upload, so I don't know what's going on there. So anyway, I'm trying to get scores updated, and then I know I'm behind in some quiz grading, but I will get around to updating some scores. I will make some comment about keeping current with WebWork in just a moment, though. Office hours still here. You can call, and I actually this morning thought of some ways I could respond in a helpful way to some of the survey comments that came up between this class, the next section, and then my 11 o'clock class, which is a different class, but like there were a number of things that came up that I'm like, this would be another, here'd be another creative solution. I don't want to get rid of office hours as I have them. I just want to provide more options and opportunities. So I'm going to like try out a couple things, and if things seem to work, you may see an email from me later today saying here's another option for office hours. There is drop-in tutoring with the Murphy Learning Center, and then today's April 20th. Here's the thing. I think what sometimes happens is people tend to fall a little behind with web work or start the assignment that's due that day. It's kind of very critical that before tuning into tomorrow's class, you really take a good go at WebWork 35. I'm not saying you have to complete it today, but if you do, that's great. But you should please give it a shot, because there's some things that we're going to look at tomorrow that are going to rely on kind of getting used to what we started last Thursday and what we continue today. So let's go ahead and take a look at those warm-ups first. We have integral of or antiderivative of 20x to the 19th dx, and we also have integral of or antiderivative of 1 over x dx. So I want to remind you of these two formulas we looked at last time. I put a recall so that these might already be in your notes if you're writing down some things. I think the key thing to remember is that you have to do something. So when you're integrating, actually, let's just see it here. So if you're given the task of the antiderivative of x to the nth dx, take a look at that n right there. Take a look at the exponent and ask yourself, is that n -1 or is it something else? So if it is -1, that happens rarely to get exactly that number -1 as the exponent. You have to do this thing. Most of the time, that exponent isn't -1, so you get to do what's over here instead. So for the first one, you can apply some of the ideas behind this right here, but because of the 20 that's already in front, it was already sort of written in a format that was maybe trying to get folks to not have to rely on this thing, but to kind of just directly think about the derivative of what thing should be 20x to the 19th, and that thing to differentiate should be x to the 20th plus a constant. The second warm-up question, integral of 1 over x dx, it's not really in either of these formats quite yet. We just need to slightly rewrite the problem. So this 1 over x that's right here, I'll circle that, is written x to the -1 right there. Now that's just an algebra step to rewrite how that looks. So that's why the integral sign is still written. That's why the dx is still written. So from one step to the next, in the second warm-up question, integral 1 over x dx is the same problem as integral x to the -1 dx. And then that's what's over here in this formula we're recalling. Now we just need to, basically copy what's right there over, and that's what you see right there with this ln of absolute value of x plus c. Finally, one other comment before moving on. This comment was mentioned last time, but it's an obscure thing, so sometimes people forget about it, but the book uses this notation on rare occasions, so does WebWork, so I wanted to just mention it. If you ever see dx over x with an integral sign in front, you could, if you just like to make it look more like the ones we've done, just kind of push the dx off to the side, so right there. So what's going on is if like problem number 2 for this warm-up is kind of the original format, where there's the integral sign on one side and this dx on the other side, you could just very well, because this dx is to be sort of thought of as a numerator quantity, kind of move it up where the 1 is, and 1 times dx up to the dx. And this notation thing is a little funky, but it will kind of preview an idea that we are going to see tomorrow anyway. So hope that looks alright for the warm-up. I'll just give a brief moment, see if we're doing okay. Again, notation going on is what's key. So let me maybe make just a bit of a copy of a slide from last time, but I just kind of wanted to change up how it was said just a little bit. Not this top part. So the derivative of what's in red, taking the derivative of x to the 10th plus a constant plus a plain old number, that's what that c stands for, gives you 10x to the 9th, right, using the power rule. So if you swap things around, so take a look at where the blue thing went. This 10x to the 9th that was in blue is now between the two bits of calculus notation, between this integral sign and the dx. Then having swapped, that's why there's this new notation for antiderivative. And then the red thing, the thing that was differentiated, ended up over here on the other side. Right, so couple comments, right? C is a constant. It's a fixed number or a frozen number. It's a number. Like C might be 28. C might be 300. I want you to, as you write a thing that looks like this, or if you read a thing like this that's written down, I want you to be saying or thinking internally, indefinite integral of 10x to the 9th is x to the 10th plus c. That's what I see here. Or if you want to take out the word indefinite and say integral of 10x to the 9th is x to the 10th plus c, fine. Or antiderivative of. I want you to see the symbol and think antiderivative of. Sometimes what happens is people don't think any words as they're writing these things down. They're trying to just go through the motions. And that's going to create a problem that I'm going to try to address on the next slide. And in addition, if you don't think that's what this symbol means as we look at what we do the rest of this week, Tuesday, Wednesday, Thursday, it's going to lead to some major problems. So I don't want that to happen. So when you see the symbol, think antiderivative of. That's probably kind of a better word, even if it's longer than integral right now, because antiderivative of, at least it's so connected to a word we've seen, namely derivative. It's anti, meaning go backwards. So yeah, if finding the derivative is going forwards, then finding antiderivative would be going backwards. I want to really make sure about some of the notation issues that go on. Like, the key thing I want you to notice here is in reporting that we are now taking the antiderivative of 10x to the 9th, like we're presenting what that is, we wrote an x to the 10th plus c without an integral symbol. So I want... Oh, goodness. Okay, so I want to be absolutely clear with this, with the following. I would like to show the mistakes on the next slide in red. Okay, so look, this presenting work properly is important. If people just kind of had morally the right answer and there would be no big issues that came from it, I'd probably let go of this, to be really honest. But making mistakes kind of early on in just showing what your final answer looks like, even if it's morally correct, even if the big ideas are there, presenting the work incorrectly is going to lead to tomorrow's thing making no sense. I know that sounds strange, but like I've thought about this carefully, and I have to say, I need to be a stickler about notation right now, and I want to be very clear about the errors that you're going to see here. So here in red, you're seeing something that's incorrect, even if morally there's a lot of the right idea there. So, but this right here, if the question was presented right here before the equal sign, integral of x to the 4th dx, or that is antiderivative of x to the 4th dx, somebody's got the right idea when they end up writing x to the 5th over 5 plus c to say that's my antiderivative, right? What would you have to... And, what would you have to differentiate in order to get x to the 4th? It's what's circled there, x to the 5th over 5 plus c. But then the question is, what is this integral sign and dx still doing? Right? So that's the problem. I want you to read that symbol as antiderivative of. You'll notice that the correct answer actually has less writing. Yeah, after the equal sign, the correct answer doesn't have an integral sign. It doesn't have this symbol here, because it shouldn't. Okay, so... If I can be as clear as possible about why what appears incorrect and why what's here is correct, it goes back to what we just said a slide ago, that when you see the symbol, read it as antiderivative of. I want you to think that. So let me say it that way. Let me just read off why this doesn't work over here. Reading the symbol every time I see it as the phrase antiderivative of. Here we go. The antiderivative of x to the 4th is the antiderivative of x to the 5th over 5 plus a constant. That doesn't work, right? So over here, reading this from the correct version, it's the antiderivative of x to the 4th is x to the 5th over 5 plus a constant. Here's another version of the error. Here's the same type of error in a different situation. we recognize that if we wrap a function in parentheses and put a prime around, that's our notation. That's one of the notations for derivative of. So I want to do the same analogy in the derivative world. This is saying that the derivative of 3 to the x is the derivative of 3 to the x ln 3. But that's not what the derivative is. The derivative of this function isn't take another derivative. The derivative of 3 to the x is, the result is 3 to the x times ln of 3, without a derivative sign on the right side. Let's do another analogy. Let's make this as down to earth as possible. Bring things really far back. 4 plus 2. You know what the answer to that is. But I will let you know from having spoken to colleagues of mine in math education who specialize in elementary education that a common wrong answer that kids will produce in writing down an answer to this question is 6 plus 2. You think I'm almost joking, but these are the things that my colleagues train some of the math education students to work with, when they work with elementary kids in the topic. You can imagine why somebody would write a plus 2, but you can also stare at this and go, wait a second, that's not what should be written, right? So this should be 4 plus 2 equals 6. That's the end of it. There shouldn't be a plus 2. And right, so we don't write this because you already plus 2. Right? So that's the same idea over here, right? So what's incorrect about having that derivative notation, that circle right there? The derivative was already done. What's incorrect about having this integral notation, which is kind of in 2 pieces, sorry, here and here? It's the integral was already done. The antiderivative was already found. Can I pause here for a second and see, like, can I clear up anything? Like this bit of notation business is extremely important, so I want to make sure we're all as happy as possible with this. Alright, what you heard last Thursday was that each derivative rule leads to an antiderivative rule. We'll look at quite a number of our derivative rules and see how we undo that derivative rule. So for instance, from back in the past, we had the constant multiple rule. So if you have k as a constant, then taking the derivative of a constant times a function is copy the constant, there's no prime on that k, and then differentiate the function. So that derivative rule leads to an antiderivative rule. So this is our new thing here, is if you have to take the antiderivative of a fixed constant times a function, that would be the same as just putting the constant in front. So you have a smaller integral problem or a smaller antiderivative problem to look at. Also, we had the sum rule and the difference rule for derivatives. So it would make sense that if you just got to take the derivative of each term separately, that you could take the integral of each term, or the antiderivative of each term separately. So this only works for pluses and for minuses. It works nicely for differentiation, so it'll work nicely for antidifferentiation to reverse the process. So here's our new things right here. And then these two, let me put them at the top of the next slide. I would suggest writing those down for reference. You could say you'll come back to the slides, but maybe it's good to just let's post those three at the top here. Next slide. Make this a little active. Also, the key things here, right? The key reference things that you're gonna probably want to have in a one-stop shop kind of place when you're working on homework. I'll just give you a moment to write some things down here, and you can work through some practice problems. you'll notice, just to point out, that there's quite a number of dx's. So the first formula has a dx on the left side and the right side. The second formula has one dx on the left side and two dx's on the right side, one for each of the integrals. So it's a little much. And you'll find that you may end up wanting to skip some of the work when presenting answers that use these formulas, and that's fine, but for maybe to start, let's just go one step at a time, just to double check the make. Alright, so let's do this all together. So the question here is integral of, or antiderivative of, 7x to the third dx. So this next text is not part of the answer, but it's really important when we're new at this to just clarify what the heck this is asking. Because I've seen this happen. I've seen people present as their answer 21x to the second, maybe with a plus c, but then what they've done is they've taken a derivative. But that's not what the question's asking. The question is asking about an antiderivative. In other words, the derivative of what thing is going to be 7x to the third. Not that you should stare at the squid and answer directly. It is possible to do that, but it's maybe a lot easier to make use of some of the ideas that we have up here and some earlier antiderivative formulas. So what I'd like to do, and I highlighted up in the top formula, the 7 in this would be the constant, right? So look at the problem we were given. It's just rewritten right at the beginning of the answer. And the point is this 7 that's red right there, that takes the place of k that's in the formula. Our f of x up here is the x cubed there. So what this first formula lets you do is it lets you take the 7 and bring this in front. Right? That's where the k ends up being right now, right? It's to the left of the integral sign. So that's what happens. In our first step of the answer, after the equal sign, the 7 has moved to become in front of the integral symbol. So take a look at the integral problem we had, and now this integral problem is smaller, right? Because there's no 7 in there, so it's a little smaller. This just means we'll do 7 times whatever we get as our final result. So then what about the integral of x to the third? Well, now we had this undoing of the power rule formula we saw last time where you have to erase the exponent. So I copied the 7, and then the antiderivative of x to the third is x to the fourth over 4, and then a plus c. And you can leave your final answer like this, that's fine, but just because some people will want to write this differently, you can write this as 7/4 x to the fourth plus c. You could also, of course, put this x to the fourth up in the numerator, so just this is fine as a final answer, this is fine as a final answer, and just to point out another option, you could have 7x to the fourth, all of that in the numerator, over 4 plus c. This is fine as a final answer as well. All three of these would be fine as final answers to this question. Just see how we're doing. Didn't answer anything. Now, one of the great things about these problems, these antiderivative problems, is you can always check your work. You can always. Why not, right? So let's go ahead and do that. So how do we check? We take what we claimed that was our final answer, and we'll take the derivative of it. So take a look at how this is written. The derivative of what was circled as our final answer. The derivative of 7x to the fourth plus c. So let's do that. Let's do that derivative. And when you do, well, it's taking a derivative. It's the number 7/4. You know, you have a number times a function, so you copy the number 7/4, and then you take the derivative of x to the fourth, which is this 4x to the third that I'm underlining at present. There's a plus. Next term is a c, but if you have a fixed number like 300 and you take the derivative, you get 0. So you can clean this up a little bit by canceling the 4's, and you're left with 7x to the third. So, and then the point is, I wanted to use some color to clarify, look, what we got was we answered the derivative of what? Fill in the blank, and that blank is right there, 7/4 x to the fourth plus c, and we ended up with 7x to the third. And going back to the question here was the derivative of what thing should end up being 7x to the third. So here's the thing, you don't have to check your work. You are not required to check your work. But it could help you detect if you had like a honest little mistake. Something might pop up a little funny, and like, oh yeah, and then it's easy to kind of, maybe somehow you copied a 4 incorrectly, or things like that. It's like easier to catch those things by checking your work. And then, perhaps more importantly for right now, I would encourage you to check your work, because checking work reinforces what this integral thing or this antiderivative means, right? The more you, like, if this is just a computation that's done without meaning, then it will lead to some problems for tomorrow and so on. So it would be a good idea to check as much as possible. What I'd like to do, unless there's questions on this, is I will keep the same 3 formulas at the top of the next problem, but let's look at it as another problem as a whole. So same 3 formulas left at the top, but here's a new problem. So now we have the integral of, or the antiderivative of, a difference. So we're going to apply this formula, where the f of x is 10x to the 4th, and the g of x is 8x to the 2nd. And if you take a look at how that gets written, it gets written as 2 separate integrals, but they're each going to be smaller. So, due to an interest of space, I didn't recopy the question. Sorry about that. I did write an equal sign to start the answer. But what you'll notice is integral sign first. There it is. Then just f of x. There it is. And then just the dx. There it is. And this minus sign is that minus sign. Then another integral sign. Okay. Then we need g of x. And we said g of x is 8x squared. And then another dx squared. That's applying this formula. And so a thing that looked like this, that's how the question originally looked. Right after our equal sign, our first step of the answer, we wrote down a thing that looks like that. We'll just pause and make sure we're okay with that. Point being, what this has done is it's taken us from one much bigger integral problem to 2 smaller integral problems. And now, for each of these problems individually, take a look. We could take this 10 and bring this in front. That's the property that we just saw in practice in the previous question. Same deal, in this integral problem, the second one after the minus sign, we could take this 8 and bring it in front. That's again using this formula we saw. And doing that is going to produce 10 integral x to the 4th dx minus 8 times integral x to the 2nd dx. Now, we still have an integral to do here. So this is where we undo the power. We've got to raise the exponent by 1 and then divide by that new exponent from the formula practiced in the warm-up. So this will be copy the 10, and then the integral of x to the 4th is x to the 5th over 5. Copy the minus sign, copy the 8. And then the integral of x to the 2nd dx is x to the 3rd over 3. Oh yeah, and then once we're done, there's no more integral signs. You just stick on a plus c. I will make the following comment that if you feel comfortable doing so, these formulas, what's being shown in the last question and this question is going as step-by-step as possible through the processes. But sometimes what happens, as people feel a little more comfortable, you might just feel like jumping directly from here to there without showing work. That'd be fine by me. But just, for now, just wanted to clarify what the processes are that we went through today. Is that when you have an integral of a sum or a difference, you get to split things up nicely as 2 separate integrals. Things won't work out also nicely if you have multiplication, for instance. So you can skip directly from, in a problem like this, if you feel comfortable doing so, skipping from the original question down to the final answer. It could be possible to do that. I will make the following comments though about this. It's like, it depends on the problem whether you can get away without showing any work. So some questions, in fact, just later this week, will require showing work. In other words, there isn't a way to really do the problems that we will look at later on in the week without showing some work. So what I'm trying to get at is, this might seem like a whole lot of work to show, and so I'm trying to just address right now, do I have to show all those steps? I'll say, no, just show a reasonable number of steps, and the point is, in some of the problems you'll see later in the week. I couldn't do them without showing some steps. I would need to write down something, like I couldn't keep track of all the things in my head for some of the questions we looked at. And then that said, if you don't feel comfortable skipping steps, don't. Or if you feel comfortable skipping some steps, but you just want to make sure, like, you can't go wrong showing just a little bit more work, right? Like, just to make sure there's no error, that you need to clarify that you're showing me how the process works. It's easier to earn partial credit, for instance, by showing your work as well. So before moving into some practice questions, I have one other group question I'd like to do here. I'd like to look at the antiderivative of x times the quantity 3x to the 5th plus 7x to the 10th dx. A common mistake that occurs in this problem is to try to take this x right here and bring this in front, thinking that it's like this k that's right there, and bringing it in front and leaving it just to the left of the integral, right outside the integral. So that doesn't work, and the reason that doesn't work, the reason we can't use this constant multiple rule for integrals is because you need k to be constant and x is not. X is a variable, so you can't just bring this x in front. So we're gonna have to do something else instead to the problem, but we don't have any, at least up here, any way to deal with the integral of a product. There is a way to undo the product rule, but we haven't talked about it. It's not quite what you think it is, and we're not going to cover it because it's, if we had like an extra 3 weeks in the semester, we would talk about it or something, but you know, it's not going to happen. So what we should do is we should distribute the x. Let's do a little algebra. Now, because the step we're going to do is algebra, we should still write this integral notation. So distribute the x. But see, the thing is, we haven't taken an antiderivative yet. We have not started thinking about the derivative of what thing should be, you know, what this. So if we have not started thinking about an antiderivative, we've just said the antiderivative of, that's it. We haven't, like, undone the derivative process. Then we should still write the integral notation. Get what I mean here? Like, there's a... You'll notice in these steps that we're doing, there are times that it seems like, why does he keep writing the integral sign sometimes, and why not other times? Every time there's a reason. So it goes back to like the same overall principle like we looked at when we first looked at limits. And there was a time of, okay, this step going from here to here was algebra only, and therefore you still wrote this neat calculus limit notation. Same thing with derivatives at some point. It's like we're not ready to take a derivative, we just want to rewrite this thing using algebra so that we can take a derivative, or so that taking the derivative will be nicer. You know, that algebra step would mean you would still write that calculus notation of derivative. Same deal here. Distributing the x to these two spots is algebra work, and so we still have this calculus notation, both the integral and the dx, both of those pieces. Now, staring at this, we are ready to talk about what the antiderivative is. So the three, I mean, again, you can split this up into two separate integral problems. I'm trying to now model, unlike the previous question, just skipping a little bit of that work. So if you split these into just integral of each of these two things separately, and then the 3 you get to copy, but you have to antidifferentiate x to the 6th. You have 3 to copy, and then x to the 7th over 7. And then plus the 7 would be copied, and then you anti-differentiate x to the 11th. That will give you x to the 12th over 12. That's why there's no more antiderivative notation in there. Oh yeah, and then at the end, whenever you're undoing a derivative, in other words, you're doing an antiderivative, there's always a plus c to represent this idea that it could be any number. That capital C could be 100, and yeah, the derivative of that constant 100 would be a 0. How does that look? Are you doing okay? Answer any questions from the crowd? I hope what you're noticing a little bit from the process of this this specific question is sometimes people just want to anti-differentiate that x part, and then this part separately, but that's not a thing, that's made up. So I want to like super clarify before setting you loose on some practice questions. I would like to look at this example. So integral of quantity x squared plus 1 times quantity x to the 5th plus 4x dx. Writing that question down, you do need that dx there. And I will just, maybe don't write down this next thing in the red box, but let me just point out that this is a very common mistake I see. What I see people do is, in order to just copy the question down right in this warning box. And what I've seen people do is they'll say, oh, okay, I'll just integrate that part and integrate that part separately. The two pieces, that's what is being represented right there. Integral of x squared plus 1 and integral of x to the 5th plus 4x. So people will just anti-differentiate each of the two parts separately and multiply the results together. That's made up. So this is the made up product rule for integrals. Remember that the product rule for derivatives was actually quite a process, right? First times derivative of the second plus second times derivative of the first. If the derivative for a product was an involved process, you can imagine that undoing it is an even more involved process. So much so we're not even going there. We will not go there this semester. In fact, most semesters I don't get to it. Anyway, we definitely will not this semester. Right? So what to do instead is to FOIL. Now, that algebra process means you should still write the integral sign and the dx. So the original question, just copied again, turns into, after an equal sign here, turns into integral of x to the 7th plus 4x to the 3rd plus x to the 5th plus 4x dx. The great thing about this is now there's a bunch of plus signs, right? And that means there's a bunch of there's 4 separate terms. And just like you would differentiate each term separately, and that works out, you can anti-differentiate each term separately, that's going to work out. So you have here, to anti-differentiate x to the 7th, you have x to the 8th over 8. To anti-differentiate 4x to the 3rd, the approach I wrote here, you'll see, is I copied the 4, and then the antiderivative of x to the 3rd is x to the 4th over 4. Of course, those 4's cancel. So whether you cancel the 4's here and here or not, I don't care. I'm not worried about whether your answer here is as simplified as possible in this situation. I just point out if you do cancel the 4's, you would just be left with that second term is x to the 4th. And some people prefer staring at 4x to the 3rd and saying, they're thinking kind of directly, what should you differentiate to get 4x to the 3rd? Oh yeah, that would be x to the 4th using the power rule. So just another way to think of it, anti-differentiate x to the 5th and you'll get x to the 6th over 6. And then anti-differentiate 4x to the 1 and you'll have 4 is copied and then x to the 2 over 2. Of course you can cancel a 2 on top and bottom. And then finally there is a plus. Okay, one more that fits in this general theme. So I'd like to look at the antiderivative of the fraction x squared plus x plus 1 all over x dx. And here as well, let me put in a warning box, a very common type of error people do. People will do this process of trying to anti-differentiate the top and anti-differentiate the bottom separately. That's what's shown here circled. So the circling is actually getting away with seeing the fraction line. That's not a thing. So this is a not equals. That's the warning. If you have antiderivative of a fraction, you can't just split things up into 2 separate antiderivatives. This is like, think again, like the analogy is when you have a fraction, you need to differentiate. You can't just differentiate the top and bottom separately and boom, call it a day. There's this thing that we had for derivatives called the quotient rule. So if you're going to undo, you'd have to figure out how the quotient rule itself would be undone. It would be a mess. And let me just say that I am not aware of a rule for undoing the quotient rule. Like that's how complicated this is. So we don't go there, and instead, this question, I'm not saying we just chuck it out. It can be done, but we just don't integrate the top and bottom separately. There's got to be another way to write this, and that's usually using algebra. So take a look, the question up there, sorry for not rewriting it because I wanted the space to work on the problem, but after an equal sign, what I have here is you can split this one fraction into 3 separate fractions, and the whole point then is, with these individual fractions you can cancel, so you'll have, this is still more algebra, so the integral sign is written again. You have integral of x squared over x simplifies to x over x simplifies to 1, and then 1 over x I wrote as an x to the negative first dx. And then you get to anti-differentiate each of these terms separately, so you have an x squared over 2, sorry, typo there, plus antiderivative of 1 is x, and then antiderivative of x to the negative first is ln about 2 times x, and then there's always a plus c when you then take the differential. I'll fix that typo before we upload it. Now what about this? We have sort of hinted at this using the warm-up last Thursday, but let's talk about this formally. So what about if you were given antiderivative of 2 to the x dx? Well, first I want to remind you the kind of thing we looked at in both the warm-up and then after the warm-up last Thursday was taking the derivative of, if you had the number 1 over ln of 4 times then the function 4 to the x, then finally plus a fixed number called c, you end up with 4 to the x. So if you swap these two around, you'll end up with integral 4 to the x dx is equal to what's in the square brackets, 1 over ln of 4 times 4 to the x plus c. Right, so if you swap the things on the two sides, instead of derivative notation, now we need antiderivative notation. That is what is written just to the right of this, so let me just reveal that. And this is nothing that's particularly special related to having 4, so you could do the same with a 5. So the derivative of 1 over ln of 5 times 5 to the x plus a plain number called c is 5 to the x. So if you swap where the derivative and antiderivative are written, you need the antiderivative notation. And so these two, I want to start having you start these as building a pattern in general of what should happen. What if it's not a 4? What if it's not a 5, right? Like what if you had a 2? So we should have a formula based off of building a pattern or recognizing a pattern here. And I would suggest we say it this way, right? So here's our integral rule for exponential functions. If you have a fixed number b, so you have integral sign and then the fixed number is the base, like you have a fixed number like 4 or 5, and then you have the exponent is the variable x dx, then following the format of what we see here, you can write it as 1 over ln of b times b to the x plus c, or you could scoot this b to the x up in the numerator, and that's the way it's written over here, b to the x over ln of b plus c. So there's two different ways to write it. You could write it like what's shown right there, or you could kind of just fix how the algebra is written so that the b dx is b dx over ln of b plus c. That's the result of anti-differentiating b to the x. So the question up there, the antiderivative of 2 to the x, well, we're plugging in b is 2, so you end up with integral of 2 to the x dx is 2 to the x over ln of 2 plus c. How does that look for everyone? I would then like to ask you to take a moment to have that integral formula. We had the one that undoes the power rule. We had talked about how you can't just integrate or anti-differentiate just each piece of a product separately. We had the sum, but we did have the sum rule and the difference rule. And I'd like you to please take a look at these 4 practice problems. I'd like to give you time to work on them. And then, 5 minutes or 8 minutes later, just check in with everybody, see how we're doing, and see if you want to move on. If you want, you can certainly unmute. You can hit to check on something. You can type a chat to each other or privately to me if you wanted to check on an answer. Oh, I forgot to mention that there was this comment up at the top, practice using the equal sign correctly. I don't mind if for your own work you even just, took away the question and read an equal sign, that's fine. But you'll see my work, I try to separate question from answer. Okay, how are we doing? More time? Discuss the answers. This is what you'd like to do. Thanks for that response. You do it? You look over. Let's give this a run though. I apologize if I didn't give everyone quite enough time. So, okay, here we go. So the first one, antiderivative of 90dx dx. This one's meant to just be a direct application of that integral rule for exponentials that we just saw. So final result after an equal sign should be 90dx over ln of 9 plus c. Please don't forget the plus c. And then I think the other comment here is please make sure that there's no integral sign anymore, right? So the integral sign I just drew in, or if I included a dx on this side, both of those shouldn't be there. So they're not, as tight with none of that extra writing is how it should look. Right? Again, when you see the symbol, please be thinking antiderivative of, just as a way to help remind yourself of what's happening. For the next one, again, for the answer work, I did make just a copy of the question right there, but then 3 is a number, and you can bring that 3 in front. And if you skip showing this next step, that's fine, but I had the space to do it, so at least for slides for people to look at later, I thought I would include that step so that 3 can come in front of the integral, so it's not part of the integral stuff, right? So boxed here, integral 5 to du. Now that's the integral problem. It's smaller, not a whole lot smaller, but it's a little smaller than what we started with for the integral, because the 3 is now outside, meaning we can just do that integral part using our new integral formula. We get 5 to du over ln of 5, and then multiply that result by 3. So we have 3 times 5 to du over ln of 5 plus c. For the third one here, the common mistake that occurs, just because of how the problem is presented, people will often just try to anti-differentiate 2x squared plus 1 separately from anti-differentiating x minus 1. Those thoughts never occurred to me when completing this question. It's not that you should anti-differentiate 2 things separately and multiply the results. That's made up work. It's not going to be the same final answer as this. Even if you simplify it, or you simplify that answer the wrong way, or this one, the answers will be actually completely different, totally different. So instead, you'll notice I did not have all the space to copy the problem again, but I did just put an equal sign to say the continuation of the question here. And you'll notice this expanding or foiling is algebra work. Therefore, here there is still the integral notation. This integral sign as well as this dx at the end. So all that happened is a foiling. And so we still have here the antiderivative of 2x to the third minus 2x squared plus x minus 1. And now that is all expanded out, and we have 4 separate terms, we can, for sums and differences, that's real nice, you can anti-differentiate each of the terms separately, just like you would normally be able to differentiate each term separately. So we'll do that, right? So the 2, this constant 2 is copied, and then anti-differentiate x to the third, and you have x to the fourth over 4. Then minus and 2 are copied, because a constant in front of a function is copied, and then anti-differentiate x squared, you have x cubed over 3, and then x to the first anti-differentiates to x to the 2 over 2, and then minus 1. Here, you could actually apply this power rule for integrals that we've been talking about, or you can, for this one, I just tend to stop and think, wait, the derivative of what thing is going to be a 1? So the minus sign already being copied. Minus is already taken care of, so it's out of my mind now. But it's like, what thing would I differentiate in order to get a 1? And it would be x. If you differentiate x, you'll get a 1. And having now done all our antiderivatives, there's going to be a plus c of 3. Okay, and then one last one here. Again, this is trying to address this kind of common error that comes up. People just try to anti-differentiate the top and bottom separately and then just stick the work together in one big old fraction. But that's made up. Instead, what has to happen here is this algebra. I didn't even show both of my algebra steps here, but x to the 8th over x squared is x to the 6th, 2x to the 3rd over x squared is 2x, x squared over x is 1, x over x squared is x to the negative 1, and then 1 over x to the 2nd is x to the negative 2. That was algebra work, and so that's why you still see this antiderivative of here. And now that you've got a bunch of separate terms, we can talk about taking the antiderivative of each term separately. So we have x to the 7th over 7 plus, copy this 2, and then take the derivative, the antiderivative of x to the first, and you have x to the 2 over 2. Of course, if you want to cancel the 2's there, you could write that in. I won't bother right now. The antiderivative of 1 is x. The antiderivative of x to the negative 1 is a way of reminding you there that you get ln of absolute value of x. The antiderivative of x to the negative 2, this one sometimes tends to get people, but you got to remember, when you're undoing a derivative, you have to, instead of lowering the exponent, you have to raise the exponent by 1. So when you do this exponent of negative 2, if you add 1 to it, you end up with negative 1 as the exponent, and then normally you have to divide by that new exponent, negative 1. And having done all our antiderivatives, there's still this plus c. Okay. I have some comments, just kind of overall, like this section, though we're done with it right now, seems a little strange, and we will continue building off of the ideas of this in the next section. So, a couple comments. Writing the dx absolutely matters. It just kind of seems to be there right now, and I get that. But if you just write integral sign dx, x to the 3 without a dx, that's not even properly stating the question here. Like, the dx is necessary. And it sounds so ridiculous right now, but you'll see in what we do tomorrow that that thing has a major role. So please just be in the habit of going back through notes from today and last Thursday, making sure that dx is there. I would say it would be ideal to look at today's homework, Webwork 35. If you can complete it, yeah, that's awesome, but even if you don't complete it, please at least start it. Please at least get through one of the questions on that. If you're always just doing the assignment that's due today, you're later now than even earlier in the semester due to how deadlines have been pushed a little bit further back. Please start Webwork 35 today. Getting through, yeah, we did a couple practice questions here, but just getting through at least some of those to help clarify some of the things that we're really going to look at and kind of run with tomorrow, it would be really good to look at Webwork 35 before turning into tomorrow's class. I will comment that what we've done is it's not so bad. I mean, it's still some work, but it's not so bad overall to reverse the constant multiple rule, the sum rule, the difference rule, and the power rule. That's what we've been working on. It's a little more work to reverse the exponential rule because of this like ln of b or 1 over ln of b, but that's a number, so you got to kind of take care of how that's going to look. But it can be done. We saw a formula for the integral of an exponential function today. But here's the thing, the product rule and the quotient rule for derivatives was really awkward, and so it makes sense that reversing these are awkward. We actually don't cover it. We don't cover the topic. So if you ever see the integral of a product or a quotient, you need to probably use algebra instead. Tomorrow, we will talk about reversing the chain rule. It's a process that's called U-substitution. It's involved. It's going to take us 3 class days. Again, the announcements, in case people are tuning into the very end of the clip here, is please keep current in webwork, and what that means for today, Monday, April 20th, is to start webwork number 35. As usual, here's the office hour times. Call in, join by WebEx, and tomorrow there is an online quiz. We'll see you for office hours at 5:30 today, or for class tomorrow, and yeah.